Welcome to episode 10 of the Semiconductor Age. In the previous episode, we saw how transistors become logic gates and circuits. But how do all these circuits work together to actually run a program? Today we go inside the CPU. CPU stands for Central Processing Unit. It is the main processing engine of a computer, responsible for executing instructions and coordinating the movement and processing of data. A CPU is not a single component doing everything. It contains several specialized parts, including the control unit, ALU, registers, and cache, all working together to execute instructions efficiently. Every program eventually becomes a sequence of instructions that the processor can understand. Instructions such as load, add, store, and jump tell the CPU what operation to perform and where the data should go. Registers are tiny storage locations built directly into the processor. They hold the data, addresses, and intermediate results that the CPU needs immediately, and they are among the fastest storage elements in a computer. The Arithmetic Logic Unit, or ALU, performs many of the CPU's basic operations. Addition, subtraction, logical operations, comparisons, and other calculations ultimately rely on the logic circuits we explored in the previous episode. But the ALU needs instructions. The control unit interprets those instructions and generates the control signals that coordinate registers, the ALU, memory, and other parts of the processor. At the heart of CPU operation is a repeating process: fetch, decode, and execute. The processor retrieves an instruction, works out what it means, performs the required operation, and then moves on to the next instruction. First comes fetch. The CPU uses the program counter to locate the next instruction in memory, retrieves it, and places it into the instruction register so it can be processed. Next comes decode. The control unit examines the instruction and determines what operation is required, which data is involved, and which parts of the CPU need to be activated. Finally, the CPU executes the instruction. The required data is sent to the appropriate functional unit, such as the ALU, the operation is performed, and the resulting value is stored or passed to the next stage. The CPU cannot keep everything inside its registers. Data and instructions move through a hierarchy, from registers and cache to RAM and long-term storage. The closer the memory is to the CPU, the faster it generally is. A processor is only one part of a computer system. It continuously communicates with memory, storage, input and output devices, and other specialized chips, moving data and instructions through the system. Now we can zoom all the way back down to the transistor. What looks like one simple instruction at the software level can trigger enormous numbers of operations inside the processor, ultimately involving billions of tiny transistor switching events. The CPU is therefore much more than a piece of silicon. It represents a remarkable chain of ideas. Physics creates semiconductors, semiconductors create transistors, transistors create circuits, and circuits create computation. Understanding the CPU is really understanding how physical laws become information technology. And that brings us to the end of episode 10. We have followed the journey from an instruction to the tiny transistor switching that makes computation possible. But there is another fascinating question. Why do modern computers need different kinds of processors? In episode 11, we compare the CPU and the GPU and discover why parallel computing changed everything. If you enjoyed this journey, like, share, and subscribe to Physical Sciences Consultorium, PSC. Your support helps us continue exploring the science behind the technology that shapes our world. Until next time, keep exploring, keep questioning, and keep discovering.